How do you choose between a substitution reaction and an elimination reaction? Because they're always in competition. Sometimes products are only observed from substitution or elimination. For example, if I had this tertiary iodide here and react it with sodium methoxide and methanol, the only product observed is the E2. This is the only product. But sometimes you get a mixture of products. If I have the same tertiary iodide, I use water and heat. I get the elimination product from E1 and also the substitution from SN1. So how do you decide? Well, first you want to determine the function of the reagent. Is it more likely to act as a base, as a nucleophile, or is it both? Then you want to look at the substrate and predict whether the expected mechanism is SN1, SN2, E1, or E2, and consider relevant regiochemical and stereochemical requirements. Do I need my substrate to be anticoplanar? Do I have a secondary? Do I have a tertiary that's going to invert stereochemistry? When we first look at determining the function of the reagent, whether or not it's going to act as a base or both, or just a nucleophile, we can think of a couple of things. Reagents that act as a strong base or weak nucleophile include sodium hydride, DBN, and DBU. You can see those reagents here. Diazobicyclonon-5-ene is DBN, and then the undecene is DBU. So these are acting as bases only. So that means that if you want to do an elimination reaction, you want to use a base only. So these are for elimination. So these don't act well as nucleophiles. They're only good for abstracting protons or acting as a base. This category over here are things that are strong bases, but can also be strong nucleophiles. So OH minus, MEO minus, and ETO minus. These are strong bases and strong nucleophiles. They can be used for elimination or for substitution reactions. Things that are weak bases and strong nucleophiles include I minus, Br minus, Cl minus, Rs minus, Hs minus, RSH, and H2S. These are things that you want to use for substitution only. Sodium bromide might be good for a nucleophilic reaction, but it is not good if you want to do an elimination reaction. So things that are weak bases and weak nucleophiles include H2O, methanol, and ethanol. When we're looking at the substrate, then we can look and see what kind of mechanism it can go through. If you use a strong base, weak nucleophile, so that is the sodium hydride, DBN, DBU, you will get an E2 reaction with primary, with secondary, and with tertiary. So anytime you're going to use sodium hydride, DBN, DBU, you're going to get an elimination reaction in the form of an E2 reaction. If you use a strong base and a strong nucleophile, so that would be the hydroxide, methoxide, ethoxide, if you have a primary, you're going to have E2 this much of the time. The majority of your product is going to be an SN2 reaction. If you have a strong nucleophile, strong base, with a primary, it's going to be mostly SN2. If your substrate is secondary, the majority of your product will be E2 and a little bit SN2. If it is tertiary, you have a strong base, that's just going to be E2. If you have a weak base and a strong nucleophile, the nucleophile will do the substitution with primary or secondary. If you have a weak base, strong nucleophile with a tertiary, that will be SN1. And then a weak base, weak nucleophile for primary and secondary, nothing's going to happen here. And with this one, we get SN1 and E1. Okay, so if we look at this first one, we have a primary substrate. Sodium hydroxide is a strong base and strong nucleophile. This is primary, so we're going to get a mixture of E2 plus SN2. This is minor. This is the major. This is secondary. We have again a strong base, strong nucleophile. The major flip-flops. So E2 is major. Substitution is minor. Tertiary with a strong base, strong nucleophile. We only get E2. There's other regiochemical outcomes that I'll let you look through here. But the great news is for you is that you will not have to decide if a reaction is SN1, SN2, E1, E2. You will need to be able to tell between SN1 and SN2 and E1 and E2, but you won't have to decide between the problems like this where it's SN1, SN2, E1, E2. If you're doing synthesis, however, you should know what is going to give you the best chance at the correct product. Okay, so for synthesis strategies, you want to know how and when to use reactions. When proposing a synthesis, you want to think backwards. If we have an alkyl halide, this is going to make an ether. So this is the forward reaction, but let's say we were trying to make this ether. This was our target molecule. We would think about how we could make an OCH2CH3 and maybe do a breakage at this position here, which can be made from an alkyl halide plus an alkoxide ion. So this is the alkyl halide that's primary. This is the sodium methoxide. This is our nucleophile. This would be the electrophile with the leaving group. So this type of arrow is a retrosynthesis arrow. That is just a backwards synthesis method. So when you perform a retrosynthesis, you provide a synthesis of a target molecule. So identify a bond that can be made using reactions that you know. So if we wanted to make this compound right here, so this is target, you might want to think about ways that you can break the bonds. If we made a squiggle line here, this is showing us is where the bond breakage is happening, or where the reaction is happening. So if I think about ways that I know how to make an alkene, so far you know how to do an elimination with something like an alkyl halide. I know that an alkyl halide is doing an elimination and forming a double bond. The halogen or leaving group can be on either of these carbons. So I can have it with the halogen here or the halogen here. So now I got to think about how I can get to the correct product. So you want to determine the expected mechanism and verify that it's reasonable. If I did the reaction with this one first, with DBU, that's going to take a proton and do an elimination to form the tri-substituted. But I could also get a bond forming here because there's an alpha proton at this position as well. If I did the reaction here and I use DBU, this will form the double bond and this will be the major product. So for the mechanism here, this DBU could grab that proton and do the elimination and kick that off. So that mechanism works out. I have the right product here. So draw the forward reaction. If you're looking at synthesis strategies, these are reactions that you should be able to do at this point. So most of these arrows starting from this alkyl halide are SN2 reactions. So if we start with sodium cyanide, we form a nitrile. So the Cn- is our nucleophile, the Br is the leaving group, this is the electrophile. The On, the carboxylate here, is our nucleophile. Here, and that forms an ester. To form a thiol, we have sodium thiol. To form an ether, we have sodium methoxide. And this is the elimination here with sodium hydride, or with t-butoxide will get you an alkene. If we react that an alkyl halide with the sodium hydroxide, that will get us an alcohol. We can convert the alcohol back to an alkyl halide via an SN1 reaction. And to go from an alcohol to a tosylate, we use tosyl chloride, which we can then use to do an elimination to get an alkene, or we can add sodium hydroxide back to it to get to an alcohol. Those were all reactions with primary substrates. To do reactions with tertiary substrate that you know about, we have the alkyl halide starting, where the bromine again is the leaving group. T-butoxide elimination will give you the Hofmann product, so that's your bulky base. If you use a smaller base with sodium hydroxide, this is tertiary, so that will force an E2 reaction. We'll get an alkene forming here. If you have an alkyl halide and you react that with water, this will go to via an SN1 reaction to form the alcohol. If you add HBr to that, that gives you the alkyl halide again. If you want to do an elimination reaction via the alcohol, this is an E1. You can do that with concentrated sulfuric acid. This one here is an E2. With the tosylate, this is an E2 reaction, and then t-butoxide is also E2, but that's with the bulky base, which will give you the Hofmann product. To go from an alcohol to the tosylate, we use tosyl chloride plus pyridine.